Today we'll be discussing gases. As you recall from our introductory lecture, the states of the matter that we will be encountering most will be solid, liquid, and gas. And while in your later engineering courses, those of you who are engineers, you will deal quite a lot with both solids and liquids. We will begin our discussion of gases in this course. We will not do much about liquids and solids here. Typically, solids are discussed more in the realm of material science and solid mechanics and things like that. And liquids are part of the realm of fluid mechanics, along with gases, both being fluids. But typically, we discuss more liquids in that course. Gases, you will also see beyond this course when you take thermodynamics. It is of vital importance in that field as well. The reason we like to talk about gases is, well, it's the simplest form of matter. So it's from a mathematical point of view and an engineering point of view, it's the easiest one to model. And as we're modeling it, we can easily describe it mathematically. And just sort of, if you look at the periodic table, most nonmetals are inherently gases. Uh, there are no metals that are gases at room temperature. Gaseous metals kind of sound a little scary. I have a few pictures here. Some of them are funny, some of them are not. Of gases, or your helium, and you see them in aerosols as household products. They are usually infused into some aerosol cans, and where you can use them as a propellant to get things out, or they are themselves in a suspension medium with another liquid or something like that. Uh, Obviously, the atmosphere around you is a gas. You emit gases through various orifices throughout your body, throughout your life. And so gases are pretty often encountered beyond just air. Okay, so let's talk a little bit about some gas properties. They are very far apart if you look at the molecules of the gases. So I have it here in the picture here in the red. Imagine each one of these is a molecule of gas. They are, relatively speaking, compared to liquids and gases, they are far apart. If you remember from the first day or two, solids are packed together, so the distance is pretty uniform and pretty consistent. In a gas, unlike a solid, they're very far from one another. They are free to move, and there's very little order and organization associated with it. And so we say, when we simplify things, we say that the molecules do not have any interaction with one another. Obviously, they do, but we say, since they're so far apart, since they're so small, they barely see each other, the probability that they'll do anything is very low. So we simplify it mathematically by saying, nah, they don't interact. So basically, if this red guy interacts with this red guy, they don't see. If they come close to one another, it's sort of like they're invisible to one another. That's sort of the simplification that we'll use here, and you will see in most of your courses with gases. Okay, we will say again, they're so small, they barely see each other, they barely interact with one another. Well, let's just do away with their volume. Imagine that the molecules themselves have no volume. Obviously, the gas itself has a volume, but the molecules, the red circles, have no volume, but they do exert some sort of a volume in this container. So there is a volume associated with a gas, but not with the gas molecules. Okay, we say that any gas would fill the volume of a container evenly. So no matter what container you put it into, it will fill the entire volume. So you could put, I don't know, like a tiny little breath of yours into the size of a room the size of, I don't know, a whole museum or something like that. We'll say that this entire thing, your little breath will expand enough to fill the whole volume. And indeed, that's true, but due to diffusion and due to the movement of the gas molecules, you will see the gases spread out evenly so that the density of the gas is even throughout the entirety of the room. Okay, we say that gases are compressible. Okay, and that's an important, a very important feature for gases. Not so much in this course, but when you do thermodynamics, you will see that when we discuss engines and cycles. You will compress the gases quite often. And you can see here in the picture here of a gas, I can push down on a gas and it will just compress, right? Here's another picture here where I can, you can see these tiny little dots are gas molecules. I can push down and then they'll become much more dense and I compress them. If I do the same thing to a liquid, that won't happen. And we say that liquids are incompressible. INCOMPRESSIBLE, incompressible. If you mix gases, no matter what two gases you mix, they will form homogeneous mixtures or solutions or whatever you want to call that. Even if, from a chemistry point of view, one of them is polar, the other one is non-polar, and they don't like one another, it doesn't matter. In a gas, because they have no interactions, because they have no volume, we say that they just form a mixture. It's just a homogeneous mixture. They just don't care. Gases are just unique like that. They ignore the rules of chemistry as well. Again, this is simplification. It's not necessarily true, but it's almost true. Okay, and gases flow. So I alluded to that in the previous slide. Gases fall in the same realm as liquids, and they're both known as fluids. They are both fluent. They both flow, and when you take fluid mechanics, you may see this in physics as well. Gases fall in that regime as well. Okay. This is just some terminology. You've seen most of it, I'm sure. When a liquid transforms into a gas, we call that evaporation. We call it condensation the other way around. When a liquid melts to form a solid freezes to form a liquid. You can also have an interaction from a solid to a gas directly bypassing the liquid altogether. And a solid will sublimate to form a gas, and a gas will deposit to form a solid. And we say that the boiling point, okay, if I hold the pressure constant, the atmospheric pressure, whatever it is, I hold it constant. If I have a liquid and I heat it up, eventually it will boil. That's the boiling point. It's the temperature at which the liquid evaporates. Another term that's thrown around a whole lot, and I wanted to define this for you very simply. I don't want you to be confused by this. There's this thing called the vapor pressure. Okay, it's the same thing as a boiling point, but instead of the temperature, you're talking about the pressure here. Okay, so if I hold the temperature constant and I push down on a liquid, and I push and I push and I push, eventually it will evaporate. Okay, I have to compress it. After I compress it for a while, it will evaporate. All right, and that pressure at which the liquid will evaporate is known as the vapor pressure. And there's nothing more to it. They're analogs of one another.